Very good evening, everyone. So, hope you are doing very well. You are covering all the lectures and you are studying as parallel to it also. So, as you all know, today's topic is chemical kinetics CBSE PYQs that we are going to practice. The questions that has been there in the previous CBSE examinations. So, let's begin with our topic, that is NCRT chapter 3 chemical kinetics CBSE PYQs. So this is the disclaimer. Let's begin with our first question. This is a CBSE PYQ and it is covering the NCRT subsection 3.3.1 under the section 3.3. Question is saying that write the rate equation for the reaction 2A plus B giving us C if the order of the reaction is 0. So basically we have given the question, and I want to mention that this is a subjective question. Okay, you have to explain it as the question were or as the question are in the CBSE examinations, right? So you have to explain properly and remember one point, that it should be better. It would be better if you explain your answer in the points rather than given in a paragraph. Okay, try to explain the points or points by points your explanation. So this question is saying that you have to write the rate equation for this reaction, which is 2A plus B, that is A and the B, which are reactant, combining, forming C as a product. It is also given that order of the reaction is 0. Then in this condition, what will be the rate equation that you have to define? So you have given some time. Try to, try to visualize this, that how you can write or how you can answer this. And then we will see its correct answer. Okay, let's see. So for this given question, so the given amount, first of all, while writing or other than the JEE or the NEET examinations, in the CBSE examinations, first of all you have to consider while writing your answer that what are the given things or what are the given quantities already present in our question, okay, which are given in the question, that you have to mention with the heading given. Okay, so what are the given thing? That this reaction is of 0 order. This is the only help we have given. So the given thing is that order of the reaction is 0. Now you can define on the given statement. Okay, so try to explain your answer on the basis of the given statements or the given quantities. So as the order is mentioned as 0, what are the properties of 0? What is 0 order reaction? So a 0 order reaction is a chemical reaction where the rate of the reaction is independent of concentration of the reactants. Okay, as we have already covered this, that as the name says, 0 means that the reactant concentration is not depending, or you can say rate is not depending on the concentration of our reactant present in our reaction. Okay, so 0 order reaction is a chemical reaction where the rate of the reaction is independent of concentration of the reactants. So the rate equation for the given reaction is 2A plus B, giving us C. Now when you have mentioned that what is the given quantity, now on the basis of given quantity you have already described that what is the zero order reaction. If we have given something more, then you can write about it too, but we have only given about the order of the reaction, which is 0. So we have mentioned the definition for the zero order reaction. Then we will conclude to the, or then we will jump to the question which we are asking. So basically the question was that you have to write the rate equation for the given reaction. So write it as that the rate equation for reaction 2A plus B giving us C, that will be R. This R is representing the rate. This you know, right? This you know. You assume that this small r is representing the rate. So rate is equals to K times, K is a rate constant, A and B concentration to the power 0, both power 0, because A and B are the reactants. So we don't mention C, because in the rate law and the rate expression we only expressed the rate of the reaction in the form of the concentration of the reactant, right? So A is a reactant, B is a reactant, so its concentration, that means they are packed in the square brackets, and their power 0 is mentioning, or their power 0 is indicating that our reaction is of 0 order. That means the rate is not depending upon the any of the concentration of the reactant. That's why we have put here 0 in the power of the concentration of the reactants. So this is the rate representation. Now you can mention that what is in this rate equation represents, that this R, what this R represents, this A in the square bracket, what it represents, what this B in the square bracket represent, and what does this K represent, and why you have put 0 in the power. This is how you can expand your answer as per the need. So for a zero order reaction, the rate will become equals to K, because something to the power 0 becomes 1. Okay, this should you know, that if something is written and it's having the power as 0, that means that whole value will become equals to 1. Something is in the power of the 0, that means its value is equals to 1. So A to the power 0 is 1, B to the power 0 is 1, K times 1 will be K. So rate become equals to the K, that is the rate constant for a zero order reaction. You can more explain it, that for a zero order reaction, therefore we can conclude that the rate of the reaction will going to be equals to the rate constant, as per this equation. Okay, so R become equals to K. This is how you can answer, and you can add up more points while answering as per your need. Okay, now let's move on to our next question. So this is a CBSE PYQ, and this is covering the NCERT subsection 3.2.2 under the section 3.2 in our chapter Chemical Kinetics in the NCERT textbook. Now the question is saying that the following experimental rate data were obtained for a reaction carried out at 25 degrees Celsius. The reaction is following like this, that A in the gaseous forms reacting with B in the gaseous forms, giving us C in the gaseous forms and D in the gaseous forms. Okay, so for this reaction which is carried out at this particular temperature, which is room temperature, the experimental rate data obtained is representing in this table. Okay, the question asked is that what are the orders with respect to A in the gaseous form reactant and B in the gaseous form reactant. So with respect to both the reactants, what are the orders that are going to be for this given reaction based on this experimental rate data. Now if you look upon this data, we have given 3 columns in this table. The first is indicating the initial concentration of our reactant A, the second column is indicating the initial concentration of reactant B, and the third column is indicating the initial rate in moles per decimeter cubic per seconds. Okay, and the concentrations are in the units of mole per decimeter cubic. Initial concentration for A reactant is given as 3 times 10 to the power minus 2. Initial concentration of B is 2 times 10 to the power minus 2. Rate initially is given as 1.89 times 10 to the power minus 4. Similarly, when you do the second experiment and change the initial concentrations of A and B, like A remains same, B will double, the B concentration will double out, and the initial rate will become 1.89 times 10 to the power minus 4. Similarly, in our third experiment, we have doubles the initial concentration of A from the previous experiment and taken the B concentration of initial as similar to the second experiment, and the initial rate coming out in this experiment is 7.56 times 10 to the power minus 4. So this is the experimental rate data of this particular reaction, and on the basis of this data you have to determine the orders of the reaction with respect to the A reactant and B reactant. Okay, so try to solve this and try to visualize that how you can answer this. Then we will see that you have given some time, and then we will see that what will be the correct way of writing the answer and what is the correct answer. Okay, let's see. So for this given question, first of all, the rate of reaction. So we have to determine the order of the reaction with respect to the both reactants present. So if you define the rate of a reaction, it can be written as R is equals to K times A concentration to the power N, P concentration to the power M. Okay, N and M have their respective meanings. So N and M are order of the reactions with respect to the A and B. So N is the order of reaction with respect to A, M is the order of reaction with respect to B from the given table. So from the given table, change the A and keeping the B constant. So your R1, okay, we are applying the condition on the given data that we have to change the A concentration and keeps the B concentration constant to get the relation between N and M. That's what we have to find out, right? So the R1 after this is coming out as K times the A concentration, let's say initial one 3 times 10 to the power minus 2 to the power N, times B concentration which we are taking 4 times 10 to the power minus 2 to the power M. Okay, we have taken from the experiment 2. You can also apply this relation on the experiment 1 or 3. Okay, so we are taking the B concentration as constant and changing the A concentration. So this is the initial rate is coming out as 1.89 10 to the power minus 4, right? Let's suppose this is the first equation. Now similarly, the R2 will become K times 6 times 10 to the power minus 2 to the power N. Now we change the A concentration and B concentration, we take it as constant, 4 times 10 to the power minus 2 to the power M. The rate is coming out as 7.56 times 10 to the power minus 4 as per the third experiment, and let's suppose this is the second equation. Okay, so for the relation between the N and M, because N and M, these are two variables, so we need two equations to solve them, right? This is a maths rule. Now what we did that we changed the A concentration and keeps the B concentration constant and use the data which is already given in the table. So the R1 will become this, and we are supposing it as first equation, and R2 will become this, which we are supposing as second equation. Now we have to divide the equation first by second to get the ratio. Okay, so when you divide the first equation by the second equation, you will get R1 by R2 is equals to K by K, 3 times 10 to the power minus 2 to the power N divided by 6 times 10 to the power minus 2 to the power N. And similarly, the B concentration to the power M. B concentration we take constant. And the rate will be 1.89 times 10 to the power minus 4 for the first divided by 7.56 times 10 to the power minus 4 for the second. Now here, if you see, when you are dividing it, this terms of the B concentration will cancel out because power is also same, base is also same, though, so this term will cancel out. K will cancel out. This you can also solve, this fraction. Okay, 10 to the power minus 4 will cancel out, and this fraction you can solve it. This 3 times 10 to the power minus 2 to the power n and 6 times 10 to the power minus 2 to the power n. You can take here 2 to the power n as common, and this will become 3 times 10 to the power minus 2. That means I am saying that when you solve this fraction, it will be going to give some answer, right? Some value. So the remaining value will become 1 by 2 because the concentration of A is 2 times or twice from the first equation in the second equation, right? In second equation, the concentration of A is twice of the concentration of A present in the first equation. That means you can write here 1, you can write here 2 because both are same, but in the second equation, we have taken the twice of the first equation. So 1 by 2 to the power n is equals to 1 by 4, which we have get from solving this fraction 1.89 divided by 7.56. Remaining things are cancelled out. The 1 by 4 is coming from 1.89 divided by 7.56. If you want to check, you can do it the calculator. Okay, if I will try 1.89 divided by 7.56, right? So 0.25 is coming, that means 1 by 4. So 1 by 2 to the power n is equals to something fraction. Okay, subfraction to the power n is equals to fraction. Okay, now you have to somehow identify the n value because n is only the variable present in this equation. So n from here is coming out as 2. How? Okay, so basically, if you reverse this equation, it will become 2 to the power minus n is equals to 4 to the power minus n, right? Now, what you put, or you can also directly conclude from this also that if you put 1 by 4 is equals to 1 upon 2 to the power 2, right? 2 to the power 2 is 4. So you can write it 1 by 4 as 1 upon 2 to the power 2. Right, that means that power thing is coming as n, which is 2, and the other thing, that is 1 by 2, is the same, that is present in the left hand side also. What does that mean? That n value is nothing but equals to 2. So we got the n value. Now for m value, m is basically the order of the reaction with respect to B, right? So this time we have to change the B concentration and keeps the A concentration as constant by using the given rate data in the tabular form. So the R1 from there become K times 3 times 10 to the power minus 2 to the power n multiply by 2 times 10 to the power minus 2 to the power m, because we have to double the B concentration. So we take the first experiment and the second experimental data, because in this experiment the B concentration is changing, meanwhile the A concentration is remaining constant. So R1 is coming out as K times this is equals to 1.89 times 10 to the power minus 4, and we are supposing it as first equation. Similarly, the R3 is coming out as, because R2 we have already identified, so R3 is K times 3 multiplied by 10 to the power minus 2 to the power n times 4 multiplied by 10 to the power minus 2 to the power m. So we double the B concentration. This is coming out as 1.89 times 10 to the power minus 4. Let's suppose this is third equation, and this is the data which we have used from the second experiment. Right, now what we do, the similar steps we have to do here. So divide the equation first by the equation third. So R1 by R3 will become K by K. This concentration of A we are keeping constant, so they are constant in the numerator and the denominator, and the B concentration is changing twice from the numerator to the denominator, is equals to this. Now if you see, this value is also same, 1.89 times 10 to the power minus 4 present at both numerator and denominator, so it will properly cancels out, and this K will cancel out. This A concentration, which is constant in numerator denominator, they will cancel out. Remaining thing is the B concentration, which is nothing but twice of the concentration in the first experiment to the second experiment, right? So you can write it as 1 by 2 to the power m is equals to 1, right? From here, the 1 to the power m is equals to 2 to the power m, right? From here, the m is coming out as 0, because if you write this equation as 1 by 2 to the power m is equals to 1, you can also write it as 1 to the power m is equals to, this 2 to the power m will go here in the right hand side in the multiplication. So 1 to the power m is equals to 2 to the power m. Now what you put in the power of the 2, that it will become equals to 1. How it will become? If I just mentioned this, that if something has in the power as 0, the value of this whole thing will be equals to 1, right? So 2 to the power something will never be 1. Only in one case, when the power is 0, that means that 2 to the power 0 will going to be equals to 1, and 1 to the power anything will going to be equals to 1, right? So m will become equals to 0. So n has came, m has came, and they both are representing the order of the reaction with respect to A and B. So with respect to A, the reaction is of the second order, and with respect to B, the reaction is of 0 order. So therefore, order of reaction with respect to A and B will be second order and 0 order respectively. Okay, moving out to our next question. So this is a CBSE PYQ, and this is covering the NCERT subsection 3.3.3. The question is assertion and reason question. Assertion statement saying that half-life of a reaction is the time in which the concentration of the reactant is reduced to 1/2 of its initial concentration. The reason? In first order kinetics, when concentration of the reactant is doubled, its half-life is doubled. So these are the statements given for the assertion and the reason. The options are that both A and R, assertion and reason, are true, and the reason is correct explanation for A. Both A and R are true, but R is not correct explanation of A. A is true, but R is false, or A is false, but R is true. So you have given some time, try to solve this. Then we will see which option will be the correct answer. Okay, let's see. So for this given question, the correct answer is option third, that is A is true, that is the assertion is the correct, but the reason is false. So half-life, we are talking about half-life of the reaction. So the half-life of a reaction is defined as the time in which the concentration of reactant is reduced to 1/2 of its initial value. So half-life, as the name has half, that means half-life of a reaction is representing the time in which the reactant concentration is reducing to 1/2 of its initial value, whatever the initially it will be, that will going to be half in its half-life. So as we know that the T half, this is the representation for the half-life of a reaction. So half-life is inversely proportional to 1 upon A naught to the power n minus 1, where for first order, the T half, that is the half-life is independent from the initial concentration of the reactant. If you remember, the half-life Okay, so in the definition it is saying that half-life is the time. Okay, half-life is representing the time in which the concentration of reactant is reducing to half of its value, right? And for first order reaction, because we are talking about the first order kinetics in the reason statement, for the first order reaction, the T half has some value, right? Has some formula in which there is no mention of any kind of initial concentration of reactant, right? That means we can say that for first order, the half life is independent from the initial concentration of reactant. Okay, now assertion saying that half life reaction is time in which concentration of reactant is reduced to one half of its initial concentration, right? But reason is saying that in the first order kinetics, concentration of reactant, when it is doubled, the half life gets also doubled. Okay, but the reason is not correctly explaining the assertion, and reason is also false, because in the first order kinetics, the half life is independent from initial concentration of reactant. Hence, we are saying that assertion, that is A, is the correct one, but reason is the incorrect one, that is the false statement. Hence, this will be the correct answer. Okay, so let's move on to our next question. Now, this is a CBSE PYQ, and we are covering the NCERT section 3.4 in this. The question is asking that what happens to the rate constant K and activation energy EA as the temperature of the chemical reaction is increased. Justify. Okay, so you have to tell that when the rate constant and the activation energy. Okay, so what will happen with the rate constant represents by K and activation energy EA when you increase the temperature of a chemical reaction? And you also have to justify your answer. Okay, so you have got your time. Try to solve this, then we will see what will be the correct explanation. Okay, so let's see. So for this given question, okay, so in the question it is mentioned that if you increase the temperature of a chemical reaction, how it will going to affect the rate constant of the reaction and the activation energy. So temperature of a chemical reaction, if it is increased, the rate constant will also increase, whereas the activation energy, that is EA, will decrease. Okay, according to the Arrhenius equation. So we define this according to the Arrhenius equation, because Arrhenius equation gives the temperature dependence or effect of temperature on the rate of the reaction. Okay, so according to the Arrhenius equation, the K, that is rate constant, is given as A to the multiply by E to the power minus EA by RT. K is representing rate constant, A is representing Arrhenius factor, E small e is the exponential factor, minus EA is representing the activation energy, R is a gas constant, and T is absolute temperature of our reaction. This is the Arrhenius equation. So from this, you can identify the relationship between the T or effect of T increase on the rate constant and the activation energy. So rate constant, that is K, increases exponentially with increase in the temperature. Okay, basically if you increase the temperature, the rate constant will going to increase exponentially. Okay, because the rate constant is defining in the terms of the exponential, or you can say exponential to the power something divided by temperature. Okay, so if you increase the temperature, if we explain more, the temperature is in denominator. So if you increase this quantity present in the denominator, that is temperature, this whole fraction is going to decrease, right? That means negative power will going to decrease of the exponential factor. That means overall value of the rate constant will going to increase. Okay, so that's how the rate constant, that is k, will increase exponentially with the increase in the temperature. If you talk about the activation energy, because activation energy is present in the numerator of this fraction, activation energy will decrease with the increase in the temperature, because if you increase the temperature present in the denominator, this fraction is going to decrease, right, with the increase of temperature. That means EA value is going to decrease. So EA decreases with the increase in the temperature, as shown in the following graph. So here the EA1, okay, so first of all, EA1 and EA2 are representations for the different activation energy for the different reactions where if the temperature is lower and if the temperature is higher. So with increase in temperature, the activation energy decreases because energy of reactant increases at higher temperature. Okay, so graph is not available at this time. Sorry for that. If we can see that, let me try. Okay, so at now we can't see that. Okay, I can explain. So basically graph is showing the difference of the activation energy when the temperature is changing. Okay, and also the graph for the EA1, that is the first reaction activation energy, is showing the greater gap, and the graph for the second reaction is showing the lesser gap for the activation energy. This is basically the Arrhenius graph we have mentioned here, attached here, which is depicting the effect of temperature on the activation energy of the graph, okay, or activation energy of the reaction. And from that we have concluded that reaction temperature will going to affect the activation energy. In which manner? That if the temperature is going to increase, the activation energy will going to decrease, because of reactant will increase the energy of itself at higher temperature. If temperature become higher, the reactant energy will also increase, due to which the gap of the reactant energy in the initial in the initial condition to the activated complex condition, that gap of the activation energy will increase or decrease with the temperature increase or decrease. Okay, so that's what the graph shows. Sorry for the inconvenience, we can't show it right now. Okay, and you can also define, or you can also understand from this given equation of the Arrhenius, which defines that the rate constant is going to affect by the increase of the temperature, and also the activation energy will also going to affect by the increase of the temperature. Activation energy will going to decrease, meanwhile the rate constant will going to increase with the increase of temperature. Okay, so let's move to our next question. So this is also a CBSE PYQ, and this is covering the NCERT section 3.3.2. The question is saying that for the reaction, okay, so question has two parts. First of all, the first part is saying that for reaction 2N2O5 converting to 4NO2 plus O2 at 318 Kelvin, calculate the rate of the reaction if rate of disappearance of N2O5, which is our reactant, is given as 1.4 times 10 to the power minus 3 molar per seconds. Okay, so in the first part of the question, we have asked that you have to calculate the rate of the reaction for this given reaction at 318 Kelvin. If we have given the value of rate of disappearance of N2O5 as this much. Secondly, the second part of the question is saying that for a first order reaction, derive the relationship of T99% is equals to 2T90%. Now, what is T99% showing? That when the reaction time is 99% done. Okay, when the reaction is 99% done and when the reaction is 90% done. So, which we have given this relationship, you have to prove that or you have to derive this relationship. Okay, so these are the two parts of the question. Let's solve them one by one. So, for this given question, so for the first part of the question, as the given reaction is already given as 2N2O5 giving us 4NO2 plus O2, right? So let's say this is first equation or first reaction. Okay, how can you modify this? So according to our question, rate of disappearance is already given, which is minus of d of N2O5 divided by dt, right? So the rate of disappearance is given as 1.4 times 10 to the power minus 3 molar per second, right? It is already given. So we have written this value, this magnitude of the rate of disappearance is equals to minus of d of N2O5 by dt. That means the rate of disappearance of the reactant. Okay. Now, according to this reaction first, the instantaneous rate, if you want to write, it will be equals to the rate of reaction equals to minus of 1 by 2 of d of N2O5 by dt. D of N2O5 is representing the small change in the concentration of reactant and d of t is representing the small change in the time. And because if you know about the instantaneous rate, which we have in the very first and the very starting studied in the chemical kinetics chapter, if you write the instantaneous rate for this reaction, this reactant having 2 as a stoichiometric coefficient, right? So this will go in the denominator. Okay, so this is how the rate of reaction or instantaneous rate of reaction can be written for this given mentioned reaction. So minus 1 by 2 d of N2O5 by dt, this is showing the rate of the reaction for the given reaction. So rate of reaction will be 1 by 2. Now this quantity, that is minus of, okay, like focus, we have already given the rate of disappearance, which is minus of d of N2O5 upon dt is equals to this much. Okay, now the rate of reaction we have find out is minus of half of change of concentration of N2O5 by dt. Now you already know the value of minus d of N2O5 by dt as this much. Okay, so we put simply here, that is rate of reaction is equals to half of 1.4 times 10 to the power minus 3. Now when you solve this, the rate of reaction is coming out as 0.7 times 10 to the power minus 3 molar per second, right? So it was the question that you have to calculate the rate of reaction if the disappearance rate for the reactant is given. So the rate of reaction will be 7 times 10 to the power minus 4 molar per second. Okay, now we will solve for the B part. So what the B part is asking, that for first order reaction you have to derive this relationship, that is T of 99% is equals to twice of T of 90%. The key concept we will going to use here is integrated rate law for a first order kinetics or for first order reaction. This also we have covered in the theory part. Now, as we know that relation for the first order reaction is k is equals to 2.303 by T log of A naught upon AT. A naught is representing the initial concentration of our reactant and AT is representing final concentration of our reactant, right? So this was the thing which we have derived from the first order rate law or first order rate equation. So the relationship between the rate constant and the time is given by this. Let's suppose this is second equation. Now, on rearranging the above second equation for the calculation of T, because we have to derive this relationship in which time is given, right? So you have to find out the equation for time, T. So T is going to be equals to 2.303 by K log of A naught by AT, right? Let's say this is third equation. Now here, the K is representing the rate constant, T is representing the time, A naught is representing initial concentration of reactant A, and AT is representing the concentration of reactant A at time T. Okay, that's why we have subscript as T. Now, the step 1 include the calculation of T 90%, that is the time for the 90% completion of our reaction. So if the reaction is 90% complete, it means that 90% of our initial reactant has been consumed, right? If we are seeing the first order kinetics, then T 90% is representing that our 90% of the initial reactant has been consumed. Therefore, remaining concentration of the reactant A, that is AT, will be 10% of initial concentration, right? Because the condition which we are talking about is T90. That means the time at which the 90% reaction is already completed. That means the initial reactant will reduced, or the initial reactant is consumed in the 90%, only 10% is remaining. So the EAT, that means the concentration of A at time T, is only the 10% of the initial concentration. Okay. So the AT, that is A concentration at time T, will be A naught, that is the initial concentration, minus 0.90 of A naught, that means 90% of A naught. Total concentration, that is initial concentration minus 90% of initial concentration that has been consumed at the T 90%. This is coming out as 0.10 A naught. Okay, this is simple. If you have any doubt, you can ask. This is simply we just subtract or we just derive the value of the concentration of A at time T as per the given conditions. Okay, so now substitute this into the integrated rate law equation, which will going to be our equation third. So the equation third we have derived was for the T. So T at 90% is going to be equals to 2.303 by K log of initial upon final. This was the formula. So initial is A naught, final is we just derived 0.10 times A naught, right? So T90 is coming out as this much. From here you can cancel out A naught, right? Now T at 90% is equals to 2.303 by K log of 1 upon 0.10, right? So according to the equation third which we have derived for the T value, where we have written T is equals to 2.303 by K log of initial concentration upon final concentration, we have just derived the final concentration value, that is the concentration of A at time T at the time where the 90% of reaction or the reactant is already consumed. Then the remaining concentration of the A is 0.10 of A naught. So we put the value log of A naught upon 0.1 of A naught. From here A naught will cancel out. The remaining thing is T 90% equals to this constant log 1 upon 0.10. Now how you can write this 1 upon 0.10? 10 to the power minus 2, right? So T 90% is going to be equals to 2.303 divided by K log of 10. So basically if you remove this decimal here, we simply remove the decimal in the denominator, or you can also do it like as I said, that 10 to the power something, and you can take it in the numerator to become the to make the power as positive. Okay, from where I should repeat? So basically in this slide we are calculating the T of 90%, right? T 90% because we have to derive this relationship which is already mentioned in the question. So T at 90%. Okay, so T 90% is representing the time for 90% completion of the reaction. 90% completion reaction means as we are undergoing the first order kinetics, 90% completion means the initial reactant is already 90% has been consumed at the T 90%. Okay, so the remaining concentration of A, that is concentration of A at time T, will be 10% of initial concentration, right? So the final concentration will going to be equals to the initial concentration minus 90% of the initial concentration that has been consumed. So remaining concentration will be only 10%, that is 0.10 of the initial, that is A naught. Okay, that is equals to the concentration of A at time T. Now when you substitute this value of the A, that is A concentration at time T, in the integrated rate law equation, it will be going to be equals to, integrated rate law equation is this equation. Okay, that is time is going to be equals to 2.303 by K is rates constant, log of final initial concentration divided by final concentration of reactant. Okay, similarly we have put the values, and from here A naught will cancel out, 1 upon 0.10 will come. This you can solve it and write it as log 10. Log 10, you know, log 10 is basically equals to 1 because log is already having base here as 10. So base, and if the base and the value are same, then it will be going to be equals to 1. So okay, so since log 10 is equals to 1, the T at 90% will become equals to 2.303 by K multiplied by 1. So T 90% is 2.303 by K. This is the value of T 90% we have derived. Let's suppose this is fourth equation. Now, the calculation of T at 99%. Okay, the another thing is T 99. T 99% means time that has been taken, or time at which the 99% completion of our reaction has been done. So if reaction is 99% complete, it means 99% of initial reactant has been consumed. The similar case, right? The similar concept. So therefore, remaining concentration of the reactant A will be 1% of initial concentration because 99% has already been consumed. So AT, that means concentration of A at time T, will coming out as A naught minus 0.99 of A naught. That is 0.01 of A naught. 1% of A naught. Now substitute this into the integrated rate law. We will get T at 99 is equals to 2.303 by K log of initial, that is A naught, upon final, that is 1% of A naught, 0.01 of multiplication of A naught. Now similarly the A naught will cancel out and the T 99% will equals to 2.303 by K log of 1 upon 0.01. You can solve it. It will come out as T 99% equals to 2.303 by K log of 100. Now A1, there is no A1, there is AT. Okay, that is concentration of the reactant A at time T. That means at 99% completion time. Now we know that log 100 you can write it as log 10 to the power 2. 10 to the power 2 means 100, right? And now here we use the log formula. That means if something is in the power in the log, that will go in the product. So it will become 2 multiplied by log 10. Now log 10 is 1, so it will be equals to 2. We put this value, so T at 99% will become equals to 2.303 by K multiplied by 2. This is the value of T at 99%. So this is the value of T at 99%, and let's say this is fifth equation. Now let's establish the final relationship. Compare the equation 4th and the 5th. Equation 4 include the value of t at 90%. Equation 5 include the value of t at 99%. So from equation 4, t 90% is 2.303 by k. And from equation 5, t at 99% is representing equals to 2 times 10 to the 2.303 by k. So t at 90% means the 90% of our reaction has been completed. T of 99% means the reaction is already 99% completed. The time at which 99% reaction is already completed. That is the T 99%. When you have given both the values, you can substitute the value of this 2.303k from the equation 4th to the equation 5th. Because in the equation 4th, 2.303 by k is t 90%. You can write it here in the equation 5, and the equation 5 will become t of 99% equals to twice of t of 90%. Therefore, t of 99% equals to twice of t of 90% is proven. That's what we have to prove. Right? That's what is given in the question, that t 99% equals to twice of t of 90%. And that's how you have to derive this. Okay, so this is step by step explanation. The same you have to follow while answering in the CBSE examinations. Okay. So that's all for today's chemistry session. Thank you so much for joining this.